You made it, it's module 7, we're halfway through the HSC course, and we're looking at Maxwell's contribution to electromagnetism. Okay, he contributed by coming up with these 4 equations here. These are his electromagnetism equations. Okay, so, and they unify electricity and magnetism. So why do we think that they should be unified? It's because of all of Faraday's experiments, right? We saw that electricity could create magnetism because any electric wires would attract magnets, would rearrange iron filings. And we know the other way around is true too, that magnetism can create electricity because Faraday showed that moving a magnet in and out of a coil can produce an electric current or an EMF. Okay, so Maxwell basically just took other people's equations and then arranged them together or compiled them together into a really neat package. First of all, this equation here, which just says for a certain amount of charge, you get a certain amount of electric field. Nice and easy. And because we're unifying electricity and magnetism, if you've got an equation for electricity, you also have sort of the mirror image equation for magnetism. This is the one for magnetism, this is the one for electric field. Okay, this one says that the overall magnetic field is always going to equal 0. Why is this? Well, because every time you have a magnet, it's always a dipole, it has a north and south. You've got magnetic field coming out and magnetic field going in, and they're cancelling each other out. The outs and the ins cancel each other, ultimately equaling 0. Okay, so far so good, nothing controversial here. The third equation is saying that is sort of just Lenz's law or Faraday's law written again. For a changing magnetic field, right? Changing magnetic field, you get a certain amount of EMF, or you get an electric field. That one's known, but here's the true genius of Maxwell. He said, if this is true, then there should be a symmetrical version that says the other way around. Why can't a changing electric field also produce a magnetic field then? And there should be some equation that describes that. So he came up with this equation here. Now, now that this equation exists, now that we know that electric fields produce magnetic and magnetic fields produce electric, we can predict the existence of electromagnetic waves. If you imagine, and it shouldn't be too hard to imagine this, if you imagine 3D space, right? It's the world you live in. You have an x-axis, a y-axis, and a z-axis. Z because I'm Australian, X and Y, right? Think of a normal wave. We've got a magnetic field and it's waving up and down along the x-axis, going up and down to the y-axis like so. As this, what I said was magnetic, as this magnetic field goes up and down, it is changing and should therefore cause a changing electric field. So this electric field will go up and down in the z-axis, so up towards the z, away from the z, and then back like so. Right? Not drawn very well there, but this, as the electric field goes up and down, the electric field, it goes back and should produce a magnetic field. So the magnetic field goes up and down, producing electric field. The electric field goes up and down, producing a magnetic field, and vice versa. Okay, this is the wave that he predicted, and this is how a electromagnetic wave could possibly go through empty space. It doesn't need any medium. The medium itself is its own field, right? It doesn't need air particles or anything like sound waves or water waves. Okay, last thing, the prediction of the velocity. So if you rearrange these equations, you can turn them into a wave equation, and the wave equation in it has a term for its velocity. And for this, if you rearrange these, you get the term for the velocity being 1 over the square root of mu naught times E naught, and that's these values here. Okay, and this is quite easy to calculate for a HSC physics student. You look at your formula sheet, your data sheet, you see electric permittivity constant, boom, this number here, magnetic permittivity constant, permittivity, 2 different words. You have this number here, and if you do 1 divided by both of these squared, you end up with the speed of these waves, and that speed ends up being about 3 times 10 to the 8 meters per second. And as Maxwell realized, this number he just produced was very, very similar to another number that they already knew about, the speed of light. So he had, by using numbers that had been discovered by studying electricity and magnetism, he had calculated the speed of light without actually measuring light at all. And this was a really, really astounding thing. You can measure these values, mu naught and E naught, much, much easier than you can measure the speed of light, which is just too incredibly fast. So we've got the production of electromagnetic waves, the propagation of them. They propagate themselves by one creating the other constantly, and the predictions made by Maxwell's theory, that is that they travel at the same speed as light. He guessed they are light, or light is them. So how did he know that it was similar to the speed of light? How had people calculated this before? And this is the third dot point we've got here. What are the historical and contemporary ways that we measure the speed of light? Let's look at those now. So, historical ways of measuring the speed of light. The first attempt that's well recorded is by Galileo, and what he did was he and a friend of his stood on the tops of two hills. Here we go, Galileo's friend. Okay, and they both had with them clocks or sand timers or something, some way of measuring time. And they agreed with each other that exactly when these sand timers would run out is exactly when they'd both flash a light at each other. And then all Galileo would have to do is time the difference between him flashing his own light out and the time between that and the amount of time it took for the light from his friend to get to him. So if you could measure the difference between those two times, he would have some measure of the speed of light. Unfortunately, he could not find hills far enough away from each other, and his conclusions were that it was either incredibly quick or it was instantaneous. He could not measure any difference in any type of speed. Okay, after that, methods got a little bit more clever. We did end up finding hills that were far enough away from each other. We used the distance between Earth and Jupiter. So let's see, let me draw this. So we have Earth, and Earth would travel around the Sun like so, and then Jupiter is also in a certain position, and Jupiter's moons are traveling around Jupiter. Now, we can record when the moon goes behind Jupiter, the eclipse of that moon, okay? And when we are far away from Jupiter, like we're here in this position, when Jupiter's moon is eclipsing itself behind Jupiter, we are further away from Jupiter. And then when later on Earth moves closer because it goes around the sun, now Earth is here. Now when Jupiter's moon eclipses itself, we are now closer to Jupiter. Okay, now this difference in distance is enough for the speed of light to have an effect, right? It took an extra 1,000 seconds for the light from Jupiter's moon to reach us when we were further away compared to when we were closer. Okay, and from that we got a value of the speed of light of about 200, 2 times 10 to the 8 meters per second, which I'd say is actually pretty good value for the actual speed of light, being much closer to 3, it's 2.299, 3 times 10 to the 8 meters per second. I think getting 2 from this method is pretty good. Okay, after that, we then developed more clever methods using mirrors to measure the speed of light. What we can do is let's see, what's one of the methods? What we can do is we can have a wheel that's got a series of holes in it, like this, and let's pretend that the wheel keeps going around. I can't bother drawing all that. And we can have a beam of light at a far distance away. We can have a light source here, which shines through the hole there. hits a mirror very far away and then bounces back towards us. Okay, and then if the wheel has been able to spin so that it blocks the light coming back, we can determine how long it took for the light to travel there and back. Okay, if we know the speed of the wheel spinning and we know the distance, a very, very far distance to the mirror and back, we can calculate how long it takes. Okay, if the wheel spun enough so that it comes back through the next gap, then that can give us even more information about the speed of light. And using this method, we can get much, much closer to the actual speeds of light. Nowadays, we just have machinery which is capable of measuring speed of light very accurately. We use laser light and we use cesium clocks, which have a very, very high degree of accuracy in terms of measuring time, much more accurate than Galileo trying with his own eyes and brain to see the speed of light himself. Now, what is the relationship to the measurement of time and distance? Distances are measured in terms of the speed of light. So we have this thing called the meter, right? 1 meter. And 1 meter used to be defined as a metal rod that was stored in a vault in France somewhere. But now 1 meter is the distance it takes light to travel in a certain amount of time. It's the distance that takes light to travel in 1,299, some other numbers. I forget exactly what these numbers are. Seconds. In that number of seconds, a very tiny number of seconds, the amount of distance light travels, that is defined as a meter. Okay, more on why we define meters that way when we get to the special relativity stuff.